Securing AI at the edge. In the field, a physical device is an open book to a dedicated attacker, without a hardware-backed root of trust. Your proprietary neural network is essentially public domain the moment it leaves the factory floor. As AI models become the crown jewels of modern enterprise, securing them at the edge has transitioned from a luxury to a functional requirement. In an AI-embedded Linux environment, the weights of a neural network represent the core intellectual property and the competitive edge of the company. From a forensic and engineering perspective, the challenge is clear: how do we protect these weights from extraction and reverse engineering if the hardware falls into the wrong hands? The technical feasibility of securing these models relies heavily on hardware-backed features like ARM TrustZone. By implementing a trusted execution environment, or TEE, typically via OPTE on ARM-based systems, we can isolate critical operations from the main Linux kernel. However, an analyst must look deeper into the architecture of the NPU or GPU. If the hardware accelerator cannot natively access the isolated memory space of the TEE, the model must eventually be decrypted into the normal Linux memory, creating a window of vulnerability. A truly secure architecture requires a secure path where decrypted data is only visible to the hardware accelerator and never exposed to the operating system. From my perspective as an analyst, any security strategy is only as strong as its weakest link, which usually starts at the bootloader. If the boot chain is not locked and signed through secure boot, an attacker can simply swap the kernel or the TEE for a malicious version designed to leak the model. Once the system is operational, we apply Linux security modules like AppArmor or SELinux to enforce strict access controls. This defense in-depth approach ensures that even if a process is compromised, it cannot reach the AI runtime or its configuration files. As a mentor in this space, I always remind teams that security is never free. Moving parts of the AI pipeline into a TEE introduces context switching between the secure world and the normal world, which inevitably adds latency. Engineers must conduct a rigorous feasibility study to ensure this overhead does not break the real-time requirements of the application. While a few hundred milliseconds of delay might be tolerable for facial recognition at a gate, it could be catastrophic for an industrial safety system monitoring high-speed machinery. Beyond the TEE, using encrypted file systems and signed model blobs offers a high level of feasibility for many modern SOCs that include a hardware security module, HSM, or TPM. The engineering task then becomes the integration of these keys into the Linux kernel keyring subsystem. Ultimately, securing AI at the edge is a multi-layered engineering challenge. It requires a holistic view that spans from silicon-level hardware box to high-level software policies, ensuring that the system remains reliable, professional, and above all, trusted in the field.